super important lesson, but this video is probably going to be a little longer than usual. I apologize, but it's important and it all goes together, so I didn't want to break it in two. This first slide is just, it says a polynomial function is anything that can be written in this degree, in this form, where you have a number times an x to a power, and it says n cannot be negative and it has to be an integer. So we're talking about like negative 7x to the 5th minus 2x squared plus 12x minus 3, etc. Okay, polynomial functions. The x's, there can't be any absolute values in there. You can't have fractions or radicals in the, basically anywhere other than the coefficients could be radicals, I guess, or fractions. Because a can be anything, okay, except 0, it says. All right. Polynomial functions are defined as continuous for all real numbers and have smooth rounded terms. This is kind of important because if you graph on your calculator and you get something that looks like it goes straight up or straight to the right or something, or has a V like this, these are not a polynomial, okay? Not a polynomial function. Like this is a negative absolute value of x that's been shifted left or right and up, etc. But that's not a polynomial function. So if you're graphing a polynomial, something like this, and you get a place where it's doing one of these things, then you have to check out what's going on the calculator, because the calculator doesn't know how to graph, it just plots points. So it will give you some very misleading graphs if you're not careful and zoom in and do all kinds of stuff. All right, shape and continuity. Polynomial functions, again, smooth curves, no breaks or gaps, continuous for all real numbers. The highest degree, n, of a polynomial is called highest exponent. Sorry, I didn't read that right. The highest exponent of the polynomial is called the degree. Polynomials are classified by their degree. So this has no x's, so it's a degree 0, it's a constant function. This has an x to the first, so it's a linear function, and x squared we've called quadratic. We have to be real careful. Quadratic and quartic, students get confused. Quadratic is a power of 2, quartic is a power of 4. And when the highest exponent power is a 3, it's a cubic. Degree 5 is a quintic. Now, these are all written in standard form, but not all polynomials come in standard form. And you have to be careful, because if I write y equals 2x to the 5th, excuse me, minus 3x to the 4th plus x to the 7th minus 9x to the 10th, this is actually a degree 10. It's with a leading coefficient of negative 9. It's just not yet written in standard form. See if that works. I think I'm gonna have to stop the video, get a drink here. Sorry, guys. All right, I think I can speak again. The power, the highest exponent power, or the degree, okay, the power meaning the degree. Okay, really? Nitro. The puppy needs a big, loud drink of water, apparently. And the coefficient, which is called the leading term, determine the end behavior of a function. Hey, that's enough. It's going to be a really good video, I can tell. All right, the graph, this says the graph you see on a calculator can be very misleading depending on your window, and that is why you need to understand these concepts. I'll explain that more in a second. But when you have an even degree with a positive leading coefficient, like you have a plain old x squared, or you have an x to the 4th minus an x squared plus 12, etc. Even degree, degree 2, degree 4, degree 6, with a positive leading coefficient, and it could definitely have like an odd number out there, it's still positive, okay? Then the shape will always be both ends up. So this one could have been doing some goofiness like this, but both ends will be up, okay? Now, we just practiced writing end behavior forever. I guess I'll write it again, but we could just say both ends are going to be up, okay? On the left and on the right. All right, if we take that same polynomial, either one of those, and we give it a negative leading coefficient, like y equals negative x squared, or y equals, now it's still even degree, so a negative 11x to the 6th plus x to the 5th, dot, 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 you will get both ends down, okay? So the end behavior might have a whole bunch of junk going on in the middle, but both ends will be down. So y will be negative on the left and on the right. All right, if you have odd degree, like a y equals x cubed, with a positive leading coefficient, so a y equals a positive 7x to the 5th minus 4, I don't know. You will have the left end down and the right end up. Now it might be doing a whole bunch of gobbledygook in the middle, but that's always what will happen. The left will go down, but the right will go up. Okay. And the last option is you could have an odd degree, like a degree 3, again. With a negative leading coefficient, it says, so maybe you have a negative 4 out front, or you have just a plain old negative x to the 7th or something. That negative takes and flips it over, so now it's going to go this way, and it might do a whole bunch of stuff in the middle, but it's still going to have the left end. As we go to the left, y will go up, and as we go to the right, y will go down. Okay? So the end behavior is determined by the degree and the leading coefficient. All right, now we got to talk about this because this is so confusing for students. We're going to have another third one yet today, but even an odd function has to do with symmetry. Okay? When we talked about symmetry, even meant y-axis symmetry, and odd meant origin symmetry. But when we talk about even an odd degree, this means like an x squared, odd degree means an x to the 5th, etc. And even an odd degree determines end behavior along with the leading coefficient. Okay, when you take into consideration the even or odd degree combined with the leading coefficient, it will tell you the end behavior. All right, let's see, next slide. So we're supposed to look at these and we're supposed to determine the power and the coefficient of the leading term given the shape. So this one, I don't know what I'm doing here, sorry. Trying to get a pen. This one has both ends down, so it has to be an even function because they're both going the same way. Even degree, sorry. And it has both ends down, so the leading coefficient has to be negative. Now, I'm going to teach you what we're coming upon here. It has 4 zeros, so it is quite likely this is at least degree 4. Okay? That's what we're going to talk about here in a minute. Now, I say at least because it's possible that there are some hidden behaviors, meaning it had some imaginary roots as well. So it could have been degree 6 or degree 8, but it's at least degree 4. And that's what we're going to go with when we do these, is we're going to assume the smallest degree possible. This one has a 0. Okay, let's go back to what we're supposed to be doing. Opposite ways it's pointing. So this would be an odd degree. Left end is down like a cubic. So that is a positive leading coefficient. Now here's the preview of what we're coming upon. There's a 0 here, there's a 0 here, but do you see how it bounces off again? Okay, we're going to talk about that as a multiplicity. And there's a 0 here and a 0 here. So even though it has 4 zeros, this one is going to have a multiplicity of 2, so it's like counts twice when it bounces like that. So this is going to be probably a degree 5. Talk more about that in a second. But it had to be an odd degree, remember. So to have 4 zeros and have this end behavior, it had to be at least degree 5. All right. This has 1, 2, 3, 4 zeros as well. So it might be a degree 4. This little hitch in here probably means it's more likely a degree 6. Because I know it is an even degree because both ends are going the same way. And both ends are going up, so it has a positive leading coefficient. All right, it's quite likely a degree 6. If you said degree 4, that would be okay too. It doesn't actually ask us what degree. I'm just trying to preview the next part of the lesson. All right. Now, we did a lesson on fancy factoring. I didn't necessarily pre-record a video. We did it in a Google Meets, and then we did it through Delta Math. You were assigned some fancy factoring. That's what I call these kind. All right, this particular one, oh, we don't even have to factor yet. I'm kidding. It's the next section. All right, all we have to do here is find the highest exponent. It is 4. The leading coefficient on that term is a 2. This is an even degree with a positive leading coefficient, so both ends will be up. Can we just write that? I really don't want to write any more end behavior statements, okay? You know how to write that by now, I hope. Over here, it is this term that has the highest exponent power, so it is degree 5 with a leading coefficient of -3. Now, normally a degree 5 looks like this, left end down, but that negative leading coefficient has flipped it, might be doing a bunch of stuff in here, but this is the shape, left end up. On the left, it's up. On the right, it's down, okay? I'll do one end behavior for you. How's that? Now, I put this here to remind myself as much as anything. This one is not in standard form. The highest exponent power is slid right in here. So this is a degree 4 with a -7 leading coefficient, which means both ends are going down. Degree 4 is even. Both ends have to go the same way. Negative leading coefficient means they go down. All right. We got to talk about turning points. Remember when you did graph analysis, we had a relative max and a relative min. We're probably just going to be lazy and call them maxes and mins. This one also has 3 zeros. Okay. These maxes and mins were called turning points. or extrema. Okay. It says the points at which a graph switches direction. Okay. If the graph is, if that's the highest point in that area, it's a max, lowest, it's a min. They are called extrema, and the turning points, or maxes and mins, indicate where it turns from increasing, decreasing, increasing. Remember, you go left to right. Okay? So this is the new part. Max and min are located at turning points. A polynomial function of degree n has at most n real zeros. Now, it doesn't always have that many. And at most n minus 1 turning points, and at most n minus 2 inflection points where it changes concavity, okay? Not going to talk a lot about that again. So on this graph, the x, what does this say? The of a function are also called, okay, the x-intercepts are also called zeros. The graphing calculator says find the zero. All right, a polynomial function of degree n can have at most n real zeros. So this could be degree 3. An even degree polynomial has an even number of real zeros or no real zeros. An odd degree polynomial has an odd number of real zeros. Now, let me just talk about that for a second. Even degree polynomial. So it could look like this, or it could look like this, or it could look like this. Okay, so this one has 3 turning points, but only 2 zeros. So this could be a degree 4 polynomial, but it would have 2 zeros. Basically, guys, a degree, even degree means both ends are going the same way, so eventually it's going to cross at least twice. And an odd degree means both ends are going opposite directions, so it's going to cross the x at least once. All right. The solutions to setting it equal to 0, setting any function equal to 0, are the zeros of the function. The solutions, they're called zeros. They're also called roots. When we get them down into this form, x plus or minus something, it's called a linear factor because this little factor is linear. So linear factors might look like this. X minus 2, x plus 5, maybe it has a squared on it, x minus 4 to the third. Okay, those are still linear factors because in the parenthesis, there are no exponents. All right, for example, given this function, what are the linear factors? We had taken x out of all that. Let's do it up here. We'll have an x, and then an x, when we take an x out, we'll have x squared plus 5x minus 24. And if you remember your factoring, x squared plus 5x minus 24 would factor 8 and 3 in any order. And to get a positive 5 out of that, we need a positive 8 and a negative 3, so that if we fold it back together, we get a negative 24. All right, that checks. So where are the zeros? If we set this equal to 0, I hope you're comfortable that either x equals 0, x minus 3 equals 0, which makes x3, or x plus 8 equals 0, which would make x negative 8. Okay, that's the slowest I'm ever going to do one of those. You should be able to look and go 0, 3, and negative 8. All right. So state the number of possible real zeros and turning points. Okay, let's see. This has to do with the degree. turning points is degree -1. We should go back and look at that real fast. Okay, when you had 3 zeros, you had 1 max and 1 min. So you had 2 turning points. It's always 1 less, okay? So this was a degree 3 or an x cubed. Had a positive leading coefficient. This means it has at most 3 zeros. I say at most because it could have 1 real 0 and 2 imaginary zeros. And that means it would have 3 minus 1 or 2 turning points or maxes and mins. All right, this particular one could be factored by grouping. They took an x squared out of this first term and that left an x plus 2. Back here they took out a -1. So they ended up with -1 times the quantity x plus 2. Let me just go through that again because I think factoring by grouping, some of you need more practice with factoring. So the first two, they took the x squared out. Then they needed that second parenthesis to be the same as the first parenthesis, so they said I could take a -1 out back here. Then they took this parenthesis out, and they never do it in the order I like, and that left x squared minus 1 back here. Now, x squared minus 1 is the difference of squares, so we could factor it further as x plus 1 times x minus 1, or any order. So the zeros were at -2, -1, and +1. So it has 3 distinct zeros, there they are, and therefore 2 turning points. Do not just graph these because you have to be able to find the zeros and you have to be able to factor eventually. All right. This is one of those tricky graphing one or factoring ones, but we're going to start first by just noticing the highest exponent power is 4. So degree 4 means it has 4 possible zeros and 4 minus 1 or 3 possible turning points. Then we're supposed to factor it to get an x to the 4th and an x squared as our only powers. We're going to have an x squared times an x squared. Factors of 18 that make 9 would be 6 and 3. 6 times 3 would give me positive 18 back here. I'd have a negative 6x squared and a negative 3x squared. So if I FOILed this back together, I'd get an x to the 4th. These would total a 9x squareds, and the negative 6 times negative 3 would be an 18. Okay, so that was just my check that it's working. So it is now factored, but we don't have nice, pretty zeros. This does not factor further, and this does not factor further, but we are smart. We can still do this. If we set this one equal to 0, we get x squared equals 6. Don't forget plus or minus when you take the square root. This one, if we set this equal to 0, we get x squared equals 3. We square root both sides, we get x equals plus or minus the square root of 3. So while they're ugly, there are 4. We have square root of 6, square root of 3, negative square root of 3, and negative square root of 6. You can list them in any order you want, but those are the real zeros. All right, scroll back up here. So this one is a degree 5. So there are 5 possible real zeros, and 5 minus 1 means 4 possible turning points. To factor this, we can take an x out of all of them. That'll leave an x to the 4th minus 6x squared minus 16. Now, we're going to take the x and leave it out front. Don't lose that one. And then we're going to factor this further because it only has an x to the fourth and an x squared. We can factor it x squared times x squared. Factors of 16 that make 6 would be 8 and 2. To get a negative 6, we'd have a negative 8 and a positive 2. And that makes a negative 16 at the back. All right, something weird's going to happen here. This one means x equals 0. This means x squared, if we set it equal to 0, would equal 8. If we square root both sides, let's see, that's square root of 4 times square root of 2. So we'd have plus or minus 2 square roots of 2. But what happens over here? If we set x squared plus 2 equal to 0, we get x squared equals negative 2. Square root both sides. You can't square root a negative number. Those are non-real. We could write I square roots of 2 plus or minus I square roots of 2, but it asked for only the real zeros. So we don't have to do those. So this graph would have only 3 real zeros and 2 non-real. Okay? So when it says possible, you're still supposed to list by degree. All right, one more try. This one is an x to the fourth. Okay, let's read the directions. State the number of possible real zeros, degree 4. So there are 4 possible real zeros. Number of turning points, 3 possible turning points. If we factor, we'd have an x squared and an x squared. Factors of 20 that make 9 minus 5 and minus 4 would give us a negative 9 in the middle. Negative times a negative would be positive 20. All right. This factors further, which wouldn't matter if we didn't factor it. We'd still get 2 when we square rooted. Whoa, that's not an eraser. This would factor x plus 2 and x minus 2. This one does not factor further. If we set this equal to 0, we get x squared equals 5. X equals plus or minus the square root of 5. If we square root both sides, set that equal to 0, we get negative 2. Set this equal to 0, we get a positive 2. So there was no i's anywhere. This is like 2.1 or something. So we have 4 real zeros. If we were trying to graph them left to right, this would be negative 2.1, and then negative 2 would be right next to that. Negative 1, 0, 1. Over here, oh, I didn't space those well at all. Over here somewhere would be positive 2, and then over here would be positive square root of 5. Okay, so there'd be 4 real zeros in here somewhere, and in between would be negative 1, 0, and 1, which were not zeros. So it was a positive leading coefficient, so it would come down through here, up through here, down through there, up through here. I don't know what it's doing in between there. Could be really high, or could go really low in between here, but that's the general shape. Because we have multiplicity of a 0 to consider. Okay, multiplicity, big word, lots of syllables. Multiplicity means how many times a 0 is repeated. Okay, and again, even and odd matter. So many ways, even and odd. All right, so repeated zeros are when you have things like x minus 2 squared, or x plus 5 to the fourth, or even an x cubed out front. This is a 0 of multiplicity 3. This is a 0 of 2, because if you set that equal to 0, you get 2, and the multiplicity up here is 2. This would be a 0 at negative 5 with a multiplicity of 4. All right, so the m up here is the multiplicity. It says the multiplicity m of a function, okay? If the multiplicity is odd, then the graph crosses the x-axis at that 0. If the multiplicity is even, then the graph is tangent to the x-axis or bounces off of. I'm going to put this on the next slide here anyway, but the multiplicity of a 0 is the degree of its corresponding linear factor. Find the zeros of the function below and state their multiplicity. All right, we can take an x out here. We'll have x squared plus 10x plus 25, which factors x plus 5 and x plus 5, which could also be written as x times x plus 5 squared. Or you could have just listed them. The zeros are at 0, -5, and -5, which means we are to write 0 has a multiplicity of 1, which we usually don't write, and -5 has a multiplicity of 2. In other words, it's repeated twice. All right, one more quick example here. We can take out a -x squared. That will leave an x squared minus 6x plus 9, which would factor x minus 3 and x minus 3. So this has a squared. So there is a 0. Now, this -1 out front is just a constant. It flips it all upside down. This has a 0 at 0 and a 0 at 3. This one is squared, so we write multiplicity 2. This one is also there twice, so it's multiplicity 2. Now, when it has an even multiplicity, like both of these did, this graph would cross or bounce at 0. It's coming up from the bottom because it's a -x to the 4th. At 0, it does not actually cross, it comes back down. And then over here at +3, it would come back up and touch and go back down. It would never cross at either 0 or 3. It would all be touching or below the x-axis. And because this is an odd, it's only there once, it would cross at 0, 0. And at -5, it would bounce. Now this was a positive cubic, and -5 is over here. So it would come up at -5, bounce, because it was multiplicity 2, and then it would cross at 0 and keep going, which would give it that degree 3 end behavior. All right, we're supposed to discover that, I think, here, and I got way ahead of myself here. If we take out an x, we have an x squared plus 4x plus 4, which factors x plus 2, x plus 2, or x times x plus 2 squared. All right, if we actually type this in the calculator, or we put in some ordered pairs, it goes through 0, 0. It has a 0 at -2. If you put in a -1 up top, you could certainly just graph it. Oh, this was squared. Okay. This would be -1. This would become a +1 times 4. This would be a -4. So we'd get out a -1. So when I put in a -1, I got out a -1. It is down here. All right, it's a degree 3, so it starts from over here down. At -2, it's going to bounce. And then it goes through 0, 0. If I put in a +1, I get 1 plus 4 plus 4, I get out a 9. So it goes up really quickly after that, okay? You can type it on your calculator if you want. All right, when the multiplicity is even, it is tangent to or bounces off. So at -2 right here, it bounced off. It did not actually cross. The multiplicity is odd. We had 0, multiplicity 1, and -2, multiplicity 2. When it was an odd multiplicity of 1 or 3 or 5, then it actually crosses the x-axis. All right, so we're going to look at these real fast. These are all nicely factored. This has a 0 at 1. If we did this equal to 0, I don't want to trick anybody here. You following me that that's a 3/2? And this would be a 0 at -4. All right. The multiplicity of, this one was 2. This one had a power of 2. And this one had nothing, so it's a power of 1. Okay? Now, the effect is that this graph would be tangent or bounce off the x-axis at 1. These are where it's doing that. This just indicates how many times it happens. When it's even here, it bounces. Or you can say tangent. This is odd, and so it will cross the x-axis. Now, this would be a nightmare, but let me go through one more thing here to graph this. It's going to have really big numbers, but if you look at what's called the leading term, this has an x and it's squared. Don't worry about the rest of what's in there. This has a 2x and it's squared. The leading term here is x and it's to the first. Well, if I think about that, that means I have an x squared, square this, and I get a 4x squared and an x. That is a 4x to the 5th would be my leading term. A 4x to the 5th means it's this shape. Okay, it starts down on the left. If I were to try to graph this, it has a 0 at 1. It has a 0 at 3/2 or 1.5. I'm not using a good scale here. And over here at -4. At -4, remember we said it crossed. It goes right through there. At 1, it's supposed to bounce. So it would come back down somewhere at 1 and cross, or bounce, I'm sorry. And then it goes up and it comes back down and it bounces at 3/2. Because that's what it said, bounce at 3/2, and it goes up. Now, is that the right end behavior for a degree 5? Left end down, right end up. All right, we're going to practice this some more, what the shape should be. Because this is what happens, guys. You get a window where you only see this piece of the graph. Well, when I only see that piece, I need to know I'm not seeing all because it does not go up on both ends. Okay, do you understand what I'm saying? This graph has to, because it's degree 5, go down on the left. All right, I'm going to undo that box so it's not so confusing in the notes. All right, one more quick one here. We can take out an x cubed, which means there's a 0 at 0 of multiplicity 3. Which is odd, so it will cross. If we take that out, we have left an x squared plus 8x plus 16, which factors x plus 4, x plus 4. So we end up with an x plus 4 squared. So we have a 0 of -4. That is multiplicity 2. So it will bounce, or you can say be tangent. So this was a degree 5 with a positive leading coefficient, and it had a 0 where it crossed and a -4 where it bounced. Because it's degree 5, it comes from the left, so it's going to bounce here and it's going to cross here. Now, I know enough from experience that when it actually does this, because this was a multiplicity of 3, it actually makes this little baby cubic shape right there, but it crosses. That's all we need to know. And then somewhere over back here, it bounced at -4. All right, so you could graph that in your calculator. You just got to watch for the window to be careful that you see all of that. All right, 3 last questions. This one says apply the leading term test, which is where you just look at the terms here. This is a negative 2x. This is a plain x, multiplicity 1, or degree 1. This is a 3x that has been cubed. We're just looking at the x part of these, because we'd have a negative 2x times x is x squared. In here, that 3 to the third would be 27, and an x cubed. We'd end up with a negative 54x to the fifth. Well, an x to the fifth is this shape, but a negative means it's flipped over. So we would end up with this shape. All right, now, and I don't really care about the 54 if you want to ignore all the numbers and just look at the fact that it had a negative, okay? Determine the actual zeros. So if we set that equal to 0, we get x equals 0, and that's multiplicity 1. You don't have to write that if you don't want. It has here a 0 at 4, multiplicity 1 again. And back here, be careful, 3x minus 1 equals 0 would mean 3x equals 1, x equals 1/3. And that one was multiplicity 3. Now, all of those are odd multiplicities, so it actually crosses at all of those places. If we were to graph it, it would cross at 0, it would cross at 1/3, and it would cross out here somewhere at 4. Now, again, a cubic multiplicity here of 1/3 would actually make it do a little cubic shape there. This was, remember we talked about degree 5, negative though, so it's coming from the top. So it does cross again, but it does a little inflection point there because of a cubic, but you wouldn't have to do that, and cross here. All right, so it said apply the leading term test, determine the zeros, and state the multiplicity. And underneath here, guys, it said, then find a few additional points. This is how Hofbauer had to graph. When I did not have a graphing calculator back when I was in school, I had to find a value in between here to figure out how low this went. And over here, I had to plug in a 2 and a 3 to figure out how high this went. You can just use your graphing calculator. So we're just going to skip this. I just want a general shape anyway, and then graph the function. All right, almost done. Take out an x or a negative x out of all these. And then that would factor x minus 4 and x plus 2. Yep, did that right? So we have a negative x cubed. So that's actually the same shape as the last one. Okay, a negative cubic is this shape, left end up, right end down. It has zeros at 0, 4, and negative 2, all of multiplicity 1. Now, negative 2 would be over here, 0 would be in the middle, positive 4 would be over here. And this shape means it's going to come from here, cross, 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 because it is all multiplicity 1. Last problem on this 45-minute video. I knew it was going to be about that long. Sorry, guys. Oh, good. This one's in factored form. So we have a negative x. If we square this, we'd get a 4x squared. I'm just looking at the leading terms now, and we have an x back here. So that would make it a negative 4x to the x, xx, and x would be x to the 4th. So even degree with a negative leading coefficient means both ends are going to be down, something like this. Then we have this. I'm going to write it over again. This means there is a 0 of multiplicity 1. If we set this equal to 0, we get negative 5/2 as a 0, or negative 2.5. and that's multiplicity 2, up here, the 2, and even multiplicity means it bounces at that. You can say is tangent to the x-axis. I'm just using words that help me remember what's happening. And then there's a 0 here at 3, and that one's multiplicity 1 again. So it crosses. All right, so I have a 0 at 0, 0 at negative 2.5, and a 0 at positive 3. And negative 2.5 is the one where it bounces. The other two it crosses. But the leading coefficient was negative 4, degree 4. So this is my end behavior. So coming from here, it bounces at negative 2.5, it crosses at 0, and it crosses at 3, which meets up with the true end behavior of both ends down. All right, those are all the concepts from this section. There are 2 slides for homework for you to do. No worksheets, no Delta Math tonight on this particular, and then we're going to talk some more about it in the Google Meets tomorrow, and then do a Delta Math assignment after we've practiced some more.